in Linux kernel, it's implemented. I mean, NAT is implemented. It's hooked on the so-called IP table. IP table is a mechanism for firewall. We will see a firewall in chapter 8, the final chapter. So IP table, with IP table, you use IP address or port number to filter packets. So it was called IP filter, but renamed to IP table. So essentially, it's a packet filter based on IP address and port number. And NAT is a mechanism mounted on IP tables. So you can mount the NAT implementation here. If you want to change the destination address, you change here. If you change the source address, you change here. So it's mounted on IP table. And you need to maintain a data structure called NAT table, which will maintain the mapping, the translation of IP address and port number. And again, it's in a hash table with a hash function of this, and then and each entry of the hash table maintain a linked list. And there's a so you do the translation on the source address or destination address, and there's a part that you need to manipulate the upper layer to look inside to see if the application layer is FTP, then you should call a set of functions to handle the translation. If the application is ICMP, then you call another set of functions. So that's the upper layer manipulation. And when you have that, you see some. You might change the sequence number. You might need to update the sequence. You might need to resize the packet or TCP header. So these are function code that would do the things we have just said, that adjust the sequence number or the packet size. Okay, and some of the implementation will be application dependent. Depends on which application. Okay, that's the end of 4.2. Next, let's have a quick look on V6, and I have only 5 minutes left, so I would just give an essential idea of V6 and then leave the detail to next week. So there are some changes on IPv6. IPv6 is to replace V4, but it hasn't. But this year you start to see more IPv6 packets running on the internet. It was 0. It was 0%. None of the packets are V6. But this year you start to see some V6 packets on the internet, but not a significant percentage, but it's getting more. And I think it would increase a little bit next year, gradually, and at some point it would grow exponentially, but I don't know when. So the address space is enlarged, much enlarged. It was 32-bit in V4, but now in V6 it's 128-bit. It's 4 times, okay, of the original size, and the space is not just 4 times. It's exponential growth. And fixed header, the header is fixed. Unlike IPv4, the header is not fixed because of the options, the option field. Here it's fixed. The reason is because that will help the processing, I mean high-speed processing of the routers. So the router prefers something with fixed format. And it has better support for QoS. That means it has a flow ID. It has a flow label in the header. And it supports auto configuration. So in V6, you don't have DHCP. You don't have DHCP. You have the auto configuration. So the idea or the essence of DHCP is embedded into V6 itself. In V4, you have V4 plus DHCP, which is a dynamic host configuration protocol, in order to do auto configuration. And DHCP is a protocol that we will cover next. It's in 2 sections away. So we'll see that next time. So with the V4, you need DHCP to do configuration on a host, on a client host, so that the client host can get an IP address. But in V6, you don't. It embeds the auto configuration mechanism into V6 protocol itself. Auto configuration, which is great, embedded. You don't need DHCP V6. No, you don't. And it supports unicast, multicast, broadcast, and also anycast. So it adds anycast. Anycast means that you want to send a packet to best one of the servers or one of the replicated servers, and you want to send it to the best, probably the shortest, the nearest server. And I don't want to. So if I want to send a packet to a destination, anycast address. Suppose Google eventually got a anycast address. Okay, and you send a packet to this anycast address, and the packet should be forwarded to one of the Google machine, perhaps in Taiwan, in Japan, in Europe, in US. You don't care. You just want one server to handle it. Then it's anycast. And this is the IPv6 header with less fields. With less fields. As you can see, if we compare this with this, the left-hand side is V4 header, the right-hand side is V6 header. And if you compare them, you see what? They remove this checksum. No need to check. I don't care. If it's in error, fine. No need to check. Some other layer will check. Either link layer. So in V6, it doesn't do any error control. The error control is only done by link layer and the transport layer at TCP. But network layer, no error control. But in V4, we still have extra error control. That is extra error control to protect the IP header. But that is extra. But not that necessary, right? So this is gone. This is gone in V6. And this is removed. This is gone. The fragmentation is in the next header. It shouldn't be here. Fragmentation should be unaware to the router. The router shouldn't be involved in the fragmentation. In V4, the routers are involved, right? The router could do fragmentation. The router does not do reassembly, but it could do fragmentation. But in V6, it says no, the router should not be involved in the fragmentation or reassembly. No. So this is gone too. And finally, TTL is renamed as hub limit. Now the name is correct, the hub limit. It was incorrect here. Now it's renamed. And this is gone. The identifier is gone. I don't need an identifier because I don't do fragmentation, so I don't need identifier. So no identification here. But I have extra field here called floor label. So for each floor, I have a label. But for packet within the same floor, they all got the same label, right? If a floor has 100 packets, they got the same floor label. But here, if a floor got 100 packets, then each of the packet will have an identifier, right? Each of the packet will have an identifier. But this is not necessary. If I don't do fragmentation, I don't need identifier. So this is gone. But I have extra field here in order to identify a floor. I want to identify a floor, but not to identify a packet. Okay. And this is gone. I don't need length. I don't need packet length. I don't need header length. No, these are all gone. And this is redefined as a traffic class. Redefine. And option is gone. And source destination address are much enlarged. Okay, so from this, you know what has been changed. Okay, the green fields are gone. And the blue fields are renamed. And new field, there's only new field, one new field, which is floor label. Okay. But how about if we want to do reassembly, what should we do? So they have defined extension header. So if I have header of this will be the most simple one with no extension header. So I have an IP header, and it says the next header, in the next header field, it says it's TCP. You put the number for TCP. Okay, so then next will be TCP header and then data. And then application header and payload here. But if I have other headers, extension header, so I would have this IPv6 header, and then next header will be routing header, and next header TCP. If I have two extension header, I would have this packet. You would say the next header is routing header, and here it says the next header is fragmentation header, and the next header is TCP. So by next header, by the field of next header, I identify whether this is a TCP header or other extension headers. So essentially, I'm putting some extra stuff to the extension header so that I can keep the header fixed and simple. Okay. And as we extend the IP address to 128 bits, we will create more levels and nodes. You will see that originally we have only 3 levels in the IP, 2 levels in the IP address, but now we can have more levels. For example, I want to give you an example. Okay. Now this is the host number. It's called interface ID here, and we call it in V4 we call it host number or host ID, and this will be network number or network ID. But now it's breakdown into 3 levels. The network could be in 3 levels. The site level, and next level, and then the top level. So I would have top level TLA, top level aggregation identifier, and then next level aggregation identifier, and then site level aggregation identifier. So I break down the network address or network number into 3 levels. Because it's so long, I can break down into 3 levels. So, so you will see that in the V6 address space, you have three levels, not just 1 level in the network hierarchy. And in V6, we only have what? Subnet, and then domain. That's all. So either it's between within a domain between subnets or between domains. So either intra-domain or inter-domain. But in V6, you would have routing. You would have routing between next level aggregation or between site level aggregation. So you create one extra level. Well, two extra. You create 2 extra levels in the hierarchy. I think I'll stop here, and next week we will start from here. Yeah, okay. So see you next week.